There has been a nuclear accident in the Soviet Union, and the Soviets have admitted that it happened. The Soviet version is this. One of the atomic reactors at the Chernobyl atomic power plant near the city of Kiev was damaged, and there is speculation in Moscow that people were injured and may have died. The Soviets may have been fairly quick to acknowledge the accident because evidence in the form of mild nuclear radiation had already reached beyond the Soviet borders to Scandinavia.
Nuclear energy, or nuclear power, is the use of nuclear reactions to produce electricity and can be obtained from nuclear fission, nuclear decay, and nuclear fusion reactions. But how does it work? There are two types of nuclear reactions: fission and fusion. But to understand how important these reactions are, we need to understand how they work. Fission is a reaction in which the nucleus of an atom is bombarded with neutrons that causes the element to become an unstable isotope, which, because of its unstable nature, splits into two or more smaller nuclei. The fission process often produces gamma photons and releases a very large amount of energy. However, nuclear fusion is a reaction in which two or more atomic nuclei combine to form one or more different atomic nuclei and subatomic particles and produces an even larger amount of energy. Just to put this into perspective, as energy is a hard thing to quantify, one fission reaction releases 1 million times more energy from a given weight of fuel than a coal or oil combustion reaction. And one fusion reaction releases the equivalent energy of 4 fission reactions. This means that the energy released in one fusion reaction is equivalent to 4 million coal or oil combustion reactions. Surely there must be a catch somewhere. I mean, it can't be a miracle fuel, can it? Well, yes, there are a few drawbacks. The biggest drawback of fission being the nuclear waste produced as products of the reactions, such as cesium-137 and strontium-90, which are radioactive isotopes, which normally are buried deep in the ground for millions of years until they are no longer radioactive. This ionizing radiation is very dangerous to life, damaging and mutating the very DNA in our cells. Therefore, it must be disposed of away from living things to reduce exposure. Another drawback to fission is the likelihood of disasters. I'm sure we have all heard of the Chernobyl disaster in 1986 as a prime example of the dangerous nature of nuclear fission reactors. Fusion, on the other hand, doesn't have any of these drawbacks. It doesn't produce any long-term radioactive waste, which doesn't harm the environment or living things. It is also much safer to react, as we will get on to later, as it isn't a continuous chain reaction. Fusion also has a nearly unlimited fuel supply, as any element, typically hydrogen sourced from water, can be used, and they can potentially be fused together to form energy, unlike fission, which requires very heavy elements which have an unstable radioactive isotope. There is one problem, however: humans haven't yet been able to harness fusion in a way which we can efficiently use energy from the reaction. This is the main problem with fusion, which is why we aren't already running on power made by fusion reactions. Fusion reactions are naturally occurring in the Sun and any star, where hydrogen atoms are fused at such high temperatures and pressure that causes them to form helium. This is how the Sun makes its energy, but you might be asking yourself, have we ever managed to create a fusion reaction? This was done in the early 1950s with the conception of the hydrogen bomb, where fission is used to create the conditions needed for a fusion reaction to take place. This was the only form of fusion with atoms on Earth until recently. However, in the 1950s, Soviet physicists Igor Tamm and Andrei Sakharov theorized the first nuclear fusion reactor, dubbed the tokamak. This tokamak uses a powerful magnetic field to confine plasma in the shape of a torus. Think of it as a donut-shaped object with many electromagnetic coils around the outside to generate and control the magnetic field to keep the extremely hot plasma in place in the center of the torus without it touching any of the sides, long enough for fusion to occur between two atoms. In the 2010s and 2020s, small-scale fusion reactions have been facilitated, And in December of 2022, the first fusion reaction, which the energy needed to be put in the reaction, equaled the energy released in the reaction, setting a precedent for the future of fusion and the possibility of earning a significant energy surplus. Currently, there are many separate international research groups, each pursuing their own approach on the method just mentioned, with a few groups researching other possible methods of fusion. Yet, there is no competitive market for fusion energy, as many research and development projects are still in the process of realizing economical, viable, and safe engineering solutions. This is being done under the oversight of organizations such as the International Atomic Energy Agency, IAEA, which oversees development of fusion energy for commercial purposes following the ITER, International Fusion Energy Organization, agreements between the United States and the Soviet Union in 1985. This also allows the top scientists of the world to work together to progress in research much faster than working separately. Although two other methods which some scientists have proposed is the so-called fusion-fission hybrid and a pulsed laser approach. The fusion-fission hybrid, like the hydrogen bomb, uses fission in tandem with fusion to produce energy. Although this is only conceptualized now and hasn't been done in real life, the pulsed laser approach alternatively uses an extremely strong laser which creates temperatures high enough for fusion to occur. In conclusion, whether we see fusion right around the corner as being the holy grail of energy, or we keep to the permanent in 20 years schedule, which scientists have been saying for the past half-century, fusion is undoubtedly the future of energy and something with enormous potential for humankind as a whole and enable us to develop further as a species whilst keeping the planet clean and preventing pollution, and above all, emitting no greenhouse gases, and thereby assisting in the push towards reaching and maintaining a net zero carbon economy.